Moskow, yes. So thank you. I want to thank the organizers for inviting me to this really nice conference. So learned a lot of things while I've been here this week. So thank you. So I'm going to talk about basically a lot of my work is in inverse problems. So in this talk, I'm going to give sort of an example of one example of an inverse problem. But the techniques here can be used for a wider class. This is I guess these are some methods that have been developed over the years, but with collaborators, and this work is with these collaborators. That's Liliana Borcea, who's at the University of Michigan, Vladimir Druskin, who moved from Schlumberger to WPI a couple years ago, Alex Mamonov from University of Houston, and Mike Zaslavsky, who's still at Schlumberger. So, okay, so what am I talking about here? So I don't come from the reduced order model community myself, but there's a lot of people who know a lot about model reduction. But it's only sort of been in recent years that reduced order models are really being used for sort of direct inversion methods. And I'll say what I mean by an inverse problem. So we'd like to see how can we use reduced order models to solve inverse problems. Why would we want to use a reduced order model? Well, there's a really, in the inverse problem I'm going to show, and in many others, there's a really, really bad inherent ill-posedness in the problem. So these are very badly ill-posed problems, inverse PDE coefficient problems. And so what happens when you have, so when I say, the underlying PDE might be a nice linear PDE for which you can get forward solutions that are exponentially converging, for example, or spectrally converging. But when the inverse problem itself is exponentially ill-posed. So what's the problem? If you just went and did a straightforward piecewise linear finite element method to solve your forward present problem or any kind of straightforward simple forward discretization, these errors in the forward model lead to extremely large errors in the inversion. So one possible fix to this problem is that if you use a spectrally converging reduced order model, so a very small order spectrally converging model can help us. And is there a way to do direct inversion methods based on that model? What I'm trying to say is if you want to get an inverse coefficient problem for a PDE, everybody knows if you just do finite differences on the PDE and try to sort of just algebraically extract the unknown coefficient, you're going to get garbage. So the approach I'm going to talk about here is to find a reduced order forward model. So given a certain type of data set, and one in which we can generally get, well, in many applications one could get, find a reduced order forward model which matches the data set exactly. And find a reduced order model. And this reduced order model would be some kind of small, low-dimensional approximation to your PDE operator. And from this reduced order model, try to extract the coefficient. So that's the general framework. And yes, so that's basically the idea. And the reason that this might sort of relate to some other things talked about here is that these reduced order models are based on rational approximation of the transfer function, at least in this spectral domain thing that we're looking at here. These are based on rational approximations of the boundary data in the spectral or frequency domain. So I'm going to mostly talk about this problem. I have some numerical results in the end, at the end of the talk for 2 dimensions, but I just want to talk about a one-dimensional problem for now because it's sort of, there's some open questions even in one dimension that are sort of hard to understand. And maybe some people here have some ideas. So this is the inverse problem I'm going to start with. And that is, consider some forward problem here where we have some spectral parameter. And this could possibly be coming from a Laplace transform of a time domain problem, for example. The simplest problem one could think of is a diffusion problem where this is an absorption parameter, and so this would be kind of an inverse absorption problem. And my domain is just the unit interval here. And I assume I have some Neumann data at the left endpoint, like a source, which is kind of equivalent to having a delta function source on the right-hand side. It is equivalent as a right-hand side to the equation. And I could put a Dirichlet boundary condition at 1 or whatever other boundary homogeneous condition I want. And I'll define the transfer function here, f of lambda, to be the solution u at the point 0. So it's as if I have a source at 0 and also a receiver at 0. And I consider the inverse problem. Suppose I'm giving some data of f. I don't know all of f. Maybe I do, but I want to extract some data. But I'm given, for example, some values of f at some sample spectral points, and also some values of the derivative of f at the sample spectral points, at those same points. And from that, I want to determine q. So again, considering this inverse problem, so given this finite set of data, find q, we will construct a reduced order model for the differential operator. That is, for if I take our differential operator to be second derivative minus second derivative plus q, construct a reduced order model for the differential operator that matches this data exactly. So, for example, and our reduced order model is going to be of size m in this one-dimensional case. So if I have, it's essentially the model of that size that's sort of the best you can do for the data because it matches it exactly. And the data is all you know. So in order to construct this model, and this is sort of some well-known stuff from model reduction theory, I can consider the variational form for this problem, and all of this extends to higher dimension, like a lot of, much more general problems. So look at solution space H1, say with the Dirichlet condition on the right, and write out the variational form for that equation, variational version of the equation. So find u in the space such that this variational equation holds for any test function phi in the space. And notice that the Neumann condition at 0 comes out as a right-hand side, evaluating phi at 0. Now, let's pretend, so for the inverse problem, we don't know q, so we cannot get exact solution, but let's pretend for a moment that we did know q, and we know these exact solutions exist. So let's pretend we were to have exact solutions, u1 through um, corresponding to these spectral points. In theory, you could construct the subspace u, which is the span of these solutions, and find the Galerkin projection of the true solution onto this subspace. So this is just standard Galerkin theory. I just look for, the solution, I'll call it UG in U, such that this holds for any test function in U. So that's standard Galerkin, and it gives us a nearest point in the energy norm, or in the H1 norm, or the energy norm corresponding to the equation, which is equivalent to the H1 norm, to the true solution. So how do you do that? I mean, I'm sorry to bore a lot everybody, but so how do you do that? Well, you look for the unknown coefficients, C, and I'm just stating this because this is also for notational purposes. I look for the unknown coefficient C. I said look for a solution in the space, and setting the test function equal to the elements of the basis, I come up with a mass matrix and stiffness matrix. And then if you wanted to solve for the forward solution in the forward problem world, you would look for the coefficient C that satisfy this equation, where the data on the right-hand side is ui at 0. Okay, so the nice thing that comes from model reduction theory is we can actually obtain this system from the data. So we can't obtain these solutions, the ui's, from the data because we don't know q. But we can obtain the system from the data, meaning we can obtain S and M. We can get it directly from the data. So this is what's nice about these methods for inverse problems, because all we have is the data. So if I go back to the variational formulation, and remember our subspace, our basis are actually true solutions themselves, so they solve the Galerkin formulation also. And take test functions to be uj, I get this equation for any I and j. So by reversing I and j and subtracting, you immediately get, it's pretty easy, that mij is just this kind of divided difference. And then by taking a spectral point and getting a limit to bi, you get that the diagonals are the derivatives. Again, looking at the variational formulation, multiplying by b sub j, reversing I and j and subtracting, I mean, you could write this down pretty easily, you get similar formulas for the stiffness matrix. And again, taking a nearby spectral point and limits, you get the diagonal of the stiffness matrix given by this derivative. And these formulas are well known in the model reduction community, and there are other versions of them. What's sort of new here is using all of this in the idea of inversion for doing the inverse problem. So this Galerkin model of small size m, which are these m by m matrices S and M, is obtained directly from the data. And this Galerkin discretization of the PDE has solutions which match the data exactly. That is, for this above described Galerkin solution UG, if we look at its transfer function, which is the resolvent basically, evaluated at 0, and call this f sub m of lambda, f sub m of lambda is the unique rational Hermite interpolant, meaning Hermite meaning matching the values in the first derivatives at those data points. If you impose it, it has to be of this form. So size m with m poles and residues. And okay, so to see why this is, for an m-dimensional test and trial space, if you do an eigendecomposition of the Galerkin problem, you can it's just easy to do a little algebra and write down the solution is given in this form, where the theta i's are the Galerkin eigenvalues and these residues are the first components squared of the eigenvectors. Or the evaluation at 0 squared of the eigenvectors. Sorry. So, and basically, so a little algebra shows you, because this is just a square matrix equation, writing the Galerkin solution at 0 is given in this form. Since the exact solutions are in the trial space, and the Galerkin method gives you the nearest point, it has to be exact. So the solution must be exact. So these must, so this Fm must equal F at those points. And then using that the exact solutions are also in the test space, you use the variational formulation and to take a little z nearby bi and take a limit, and you get the derivatives are also satisfied. It's because those exact solutions are in both trial and test space. So the derivatives of f are matched as well as the values. So that's 2m data points that this rational function matches, and so then uniqueness follows from the uniqueness of this Borcea interpolant to f. Okay, so the thing that's pretty interesting is you may say, and people see this talk in inverse problems and they sort of don't like that the data is of this form for one reason or another, because I don't know, there's a derivative and you have to have this, but the nice thing is that there are similar equivalences that hold for other data types. So like I just went through here, this Hermite data corresponds to a Galerkin space of exact solutions at these points. And then, or if you didn't like having derivatives, you could take 2m interpolation points, and then you get a Galerkin-Petrov system, that is where you have different trial and test spaces. And you could take the first m exact solutions in the trial space and the second m in the test space. And you'll get that your Galerkin solution is the interpolant to f at those two endpoints. Your Galerkin solution, if you look at it at 0, you evaluate the transfer function there, you get that that's what that is. So it matches your data. Or you could do simple PDE, which you're matching all the derivatives all at one point, and then you also get a Galerkin method with the first m derivatives of the exact solution at B, but I mean derivatives with respect to lambda. And perhaps the most interesting one, which is useful for wave problems, is that if you're given poles and residues, that corresponds to doing a Galerkin method where the space consists of the first m eigenfunctions. And so then you're matching the poles and residues of the transfer function. And you can also do any combination of above, and there's some examples that have been done in the past where pole matching is combined with some kind of multi-point PDE, and then so you can get varying regions where this approximation is good. So recall that the reduced order model is solving this equation with this Galerkin space for ui being the exact solutions at these same points where you're reading your data. And so the Galerkin system is this one, where f is your data, you can get S and M from the data, and then you could solve for C, for any lambda you want. And the C's that you solve for give you coefficients of the solution. You can get all that from the data. I just said this. So then the question becomes, how do you extract Q, which is unknown, from S and M? S and M, they may be small, but they're full and highly nonlinear in Q. So the idea is as follows. Orthogonalized so that M is the identity and S is sparse. So we'll do Lanczos orthogonalization on this problem. So how to do this? Well, so we don't want to use this basis. It's a bad basis. So let's take a delta function and project it onto U and use this as a starting vector. So our delta function corresponds to some coefficients. And then I'm going to let, use as my operator M inverse S, because M and S both play a role. You'll note that A is not symmetric, but it's Hermitian with respect to the M inner product. Symmetric with respect to the M if you put M into the inner product. And consider this basis consisting of powers of A, the Krylov subspaces. And do Gram-Schmidt on this basis. So this is the Lanczos process. It's very well known. Experts in here. And so orthogonalize with respect to, do Gram-Schmidt with this basis with respect to the M inner product. And the reason I like doing it this way is because it yields continuous L2 orthonormality because of the choice of the M inner product. You're going to get that the functions after you normalize are not orthogonal in the discrete sense necessarily, but in the sense of continuous L2. So what happens after you do this? You get a new basis for U. And we can redo the Galerkin system in this new basis. So what happens to the system in the new basis? The mass matrix, which was just the L2 inner products of the basis functions, is now the identity. The stiffness matrix, now recall A was M inverse S, and because it's a Lanczos process, the matrix A in the new basis is going to be tridiagonal. And that you could write down and see what happens. That's well known. It's like the three-term recurrence that you get from orthogonal polynomials. So the stiffness matrix will be tridiagonal because it's a Lanczos process. And the right-hand side will be non-zero only in the first component, like an approximate delta function. And then we get a basis. And you'll excuse me, I still have, so in this picture here, I have a finite difference grid because many years ago when ideas like this, we used to work with the reduced order model that was basically a finite difference grid. So I'm not talking about that in this talk, but the point is that if you look at the basis functions, the new basis functions after orthogonalization, they're sort of localized, and they sort of coincide with where these grid steps were. But basically, you've got a somewhat localized new basis to solve your problem. So it's a better basis because you have some kind of geometric information from the basis. And you'll notice you have source and receiver at 0, so your data you're reading is all over here, and it makes sense that you're going to have more refined information near where your source and receiver are. So, and basically this model here is equivalent to what are called spectrally matched grids or finite difference grids, which give the same approximation of the transfer function. So the entries of this reduced order model, which can be obtained from the data, are the entries of this stiffness matrix and mass matrix, which is and M hat is just identity. And the key, and this is where there's something I think that's really important to understand that we don't completely understand yet, is that the orthogonalized basis functions seem to depend extremely weakly on the coefficient, on Q. Remember, you don't know Q, and that's what you're trying to determine. And from the data, I can get S and M, and I can orthogonalize, I can solve for the coefficients, but I don't have the basis, because the basis depends on Q. But once I orthogonalize, I find that the basis depends on Q so weakly that one can actually use the similarly orthogonalized basis from a reference medium as your basis here. And once you have that, there's a lot of different things you can do. So the idea, which was originally done from papers by Borcea, Druskin, Mamonov, and Zaslavsky, and they were doing things mostly in the time domain. And things are a little bit different there, but it's the same idea. Since these appropriately orthogonalized basis functions depend only very weakly on the unknown coefficient, we can use similarly orthogonalized basis functions for a known reference medium. And these localized basis functions have natural extensions. So everything I've done, there's no reason it's 1D, and there's no reason there's just sources like that, just one source. So I'll say something about that afterwards. So as a numerical example, consider this problem with Q corresponding to reference problem Q0 equals 0. And here I believe Q is in the next picture. Oh, no, wait, that's not the next picture. And we read the data, samples of the transfer function f of bi and f prime of bi for these m points for the perturbed problem. Generate the m by m stiffness and mass matrices for the basis of exact solutions. Do the Lanczos orthogonalization to generate the orthogonalized system. And then look at this new basis you get. And I don't know if you can see, but this is here, this is an example with m equals 6. And the perturbed medium basis and the reference medium basis are both plotted on all of these. This is the first function, second, third, fourth, fifth, and sixth basis functions. So they're really, I mean, they're indistinguishable. This was a jump from 0 to 0.2. So, I mean, it's not, but even when you stretch out a lot, you see these things coinciding like crazy. And so this is the really interesting part of it from the point of view of inverse problems. So from the data, we have a low-dimensional reduced order model for the internal solution. Oh, wait, I didn't finish explaining that. Oh, so because because I claim we can use these reference basis functions, we can actually get the internal solution. Well, not exactly, but some approximation of the internal field, the internal solution. So by solving the Galerkin system, we get the coefficients. And so this yields boundary data generated internal solutions. So that's very interesting because in most of the inverse coefficient problems are, they're boundary data to coefficients, and it's a lot of the ill-posedness is contained there. There are people who do hybrid inverse problems where they're using multi-physics methods, et cetera, and have developed a lot of methods to do inversion based on internal solution. And there's a lot that's been shown that's very stable once you have internal solutions. So getting internal solutions are interesting from this point of view. And they could be interesting for applications in their own right. So here's with this same example, we could look at the data-generated internal solution. So I have a zoom in on the next slide. So plotted here for lambda equals 3 is a data-generated internal solution, and the exact solution are blue and red, which you can't distinguish. And then the yellow is the reference medium solution. So just to be honest, because the reference medium and the true solutions don't change that much, but you can see as you zoom in that the data generated and exact solutions are really on top of each other, where the reference medium solution is different. So the question is this different enough in order to recover Q? So how to use the internal solution to do inversion? And, well, one sort of stupid thing you can do, but why not give it a try, is just look at, so because these are diffusion problems, these solutions are positive, and we don't have to worry about zeros in the denominator, you can just do this. So let's see, and we can do this for any spectral value we want. And here's the recovery of the unknown Q in this case. I mean, if you're, so because these problems are so badly ill-posed, you're always going to, you can never get sharp pictures with inverse diffusion like this. It's just not possible to get sharp pictures. So this is actually a good picture of Q. Here's a harder example. Remember, we're only having source and receiver on one end. So, I don't have too much more. Source and receiver on one end, so you're going to read things better over here than over here, and we're seeing that. This is a sort of one with bigger difference from 0 for Q is this function. And here's a recovery. So what do you do in higher dimensions? So it's basically exactly the same thing, except now we can put, so if you're familiar with the Calderon problem, you assume you're reading the Neumann to Dirichlet map. That's for a different PD setup, but similar. So you want to probe with different Neumann functions and read U on the boundary. So you want to think of G's as your sources, and then you want to, at different spectral values, B sub I. And then now your spectral data, we're going to take it in the form of reading the solution on the boundary against the source. So assume I have a local, like G is somewhat some kind of approximate delta. That's your sort of a source, or G can be whatever you want it to be. And you just need to assume that you can read solution on the support of your sources. And then you get a block transfer function. And you're sampling that at some m points and the derivative at some m points. So now it's a k by k block. So you have m spectral values and k sources / receivers. And then you can, again, generate the Galerkin system with the basis of exact solutions. I'm almost out of time, so it's same formulas, basically. You can orthogonalize again, but now with block Lanczos orthogonalization. And after orthogonalization, the basis functions are close to those from the reference medium again. And then this will yield internal data, and we could try again. And here are just a couple pictures. Here's one where I have a 1D varying thing, but I didn't assume I knew that, and I only had 2 sources receivers. Here's my recovery. Here's one guy where I have 4 sources on just one side, so it's not a full data set. And here's the recovery. Here is recovering 2 things. This case, I have 8 sources, 2 on each side. And here I'm comparing internal solutions. This is the true, this is the reference medium internal solution. This is the true internal solution, and this is the data generated one. The difference between the true and the data generated is like 4 times 10 to the minus 3, and where the difference between the true and the reference is like 8 times 10 to the minus 2. And here's a recovery of the 2 bumps from this. And this is just sort of, and this is just using crude simulations with MATLAB's PDE toolbox. I think it would be better if I do some better simulations. So we can use spectral data to generate Galerkin reduced order model. And the point is that you get a, after orthogonalization, you get a basis that seems very independent of the medium. So one of the things I want to do is make that rigorous and understand that fully. I think that's the important problem here. That's the piece that's sort of missing mathematically. And then you can do reconstructions directly like this, but my collaborators are doing other things where they're using optimization to do the reconstruction. So there's many other ways to do the reconstruction besides this sort of simple trick. But so, and then there are extensions to lots of other models. As long as you have this kind of nice linear variational form, you can do this kind of equivalence. So that's all. Thank you. Yes.
A couple of quick questions. So one is, can we bootstrap this and use your one step and you have to get a better set?
Absolutely. Yeah. Yeah. In fact, that's yeah. So this is just again right. So this is sort of a direct method, which you always think of a direct method as just being there to feed into some kind of iteration. So yeah, I mean, I think that's definitely. Some of my collaborators have done that with wave problems in the time domain, and they've gotten some really nice results. They can be any combination. You do need, for this to work the way I've said here, you do need to be able to read data where every source is. We're working on some ways to somehow they, I mean, so yeah, so if you really, so if you're, you mean you can't really read your data in that whole region, you're saying? Okay, so then, yeah, so actually, so we're working on, I know there are some applications where you do have sources and receivers in the same place. We're working now on putting sources in one place, receiver in another. And actually, this could be a complex analysis question, because we think one of the issues is that it's not clear that when you do the rational approximation, it's not clear that, so at least in 1D, so this would be analogous in 1D, putting a source here, reading the source at 0, and you read at 1. I don't believe that, we're not sure if you do that, and this is one of the things I want to go test, if you're going to get real poles, if you try to do the approximation, which might hurt your stability. But maybe in the complex analysis community, that's not an issue. But we said, yes, thanks. Mm-hmm.
What serves as the regularization parameter?
Yeah. Right, so so that's a really good question. I would like to understand that a little bit better. M itself is very, very badly conditioned, the mass matrix that you get. That's extremely badly conditioned, and that really limits what you can do. And so sort of you're automatically regularizing because there's only so many. You have to invert M here. So I think that's the main place your regularization is. You don't have to go in and do another regularization anywhere. Yeah, I don't know. I don't have a systematic thing for that. Right. How many? How many? So M or K? You mean? So this right. So in the 2D pictures, this one has 6. M is 6, and K is 8. Yeah. And M is, I think M was, I forget what M is with this. It's always between 6 and 10, M. Yeah.
Okay.
Mm-hmm.